class 12th, in the previous lecture, we have discussed about the interference of light. That is, when the two light waves superimpose each other, then at the point of superposition, the intensity of light will be maximum or minimum. That this depends on their phase difference. So if they are coherent means both wave must have the phase difference throughout the motion constant, or the phase difference throughout the motion 0. So that two wave will be called, they are in coherent. So then only the interference phenomena will happen. If they are meeting in the same phase, then at that time there will be maximum intensity. If they are meeting in the out of phase, so there will be minimum intensity. So what should be the phase difference? Means we have discussed about that the maximum intensity will be when they are meeting in same phase. So and one more thing, I am saying that the waves must be coherent. Coherent means they can have the constant phase difference also. So how much constant phase difference they can have, we have seen in the last lecture. Again I am reminding you, if the phi, the phase difference, is equal to 0, 2 pi, 4 pi, 6 pi and so on, then you will say there will be maximum. Means if the two light waves are superimposing it at any point, then if the phase difference between the first wave and second wave is of 2 pi, 0, 2 pi, 4 pi and so on, then you will say there will be maximum intensity. Or in general, if you say that phi is equal to 2m pi, where m is equal to 0, 1, 2, 3 and so on, then at that time there will be maximum. And when will be minimum intensity? If the phase difference phi is equal to pi, 3 pi, 5 pi and so on, then at that time you will say there will be minimum intensity. Means again I am saying the two waves which are superimposing, if the phase difference between the first wave and second wave will be of pi, 2 pi, pi, 3 pi, 5 pi, means odd number of pi, then at that time there will be minimum intensity. Same way it has the equation for the path difference also. If the two waves are meeting at any point, as you can see here, the two waves are meeting at point at P. If this point P is having the path difference, means S2P and S1P, difference of them, if it is having the path difference of x is equal to m lambda, m is what? 1, 2, 3, 4, maybe anyone, means if the path difference between the waves are lambda, 2 lambda, 3 lambda and so on, then at that point P there will be maximum intensity, means constructive interference. And if there is a path difference of 2m minus 1 lambda by 2, that is lambda by 2, 3 lambda by 2, 5 lambda by 2, then at that time, that point at point P, there will be minimum intensity, or you can say destructive interference. Today's topic is very important in the sense of board examination. Why? In board examination this topic comes, means alternate year, or you can say frequently this question comes, that find the fringe width or angle between the fringes, or means simply we can say the position of maxima and minima using Young's double slit experiment. We are going to perform today Young's double slit experiment. For that, you can see here, this is a single source of light. We are going to show the interference of light. To perform the interference, we need two sources. Single source cannot perform, okay? If we are taking the two sources, two different sources, so it is impossible, means it is very difficult to have both the sources of constant phase difference. They definitely will have the difference in their phase. They will be out of phase, there will be at least 1 degree of phase difference they must have. How to make two sources of same phase? Why we are making the sources in the same phase? Because you know that the condition for the interference, that is the sources must be coherent. The two sources must be coherent. So both the sources must be coherent. If you are using two different sources, they will not be coherent. So that is why we are using first a single slit in front of the source. A single slit, a narrow hole, makes this source of energy, means the wavefront generated from here will be spherical. Then this becomes point source from the hole. Then again spherical wavefront. Then further we are using the double slit. That is why this experiment is having the name Young's double slit experiment. So this is having the double slit. Then further the light aheads and is split into two parts. It makes the two different sources. Now the origination according to Huygens principle, what is that? The secondary wavelet will be proceeding with the same speed as the original wave. Same way here also. The two different sources right now made from the single source is now having the same phase because it is developed from the same wavelet, same wavefront. So they both will have the same phase. Now further, as you have seen in the last diagram, just few seconds ago, you have seen the diagram was made up of spherical wavefronts. Now I'm not going to do that. I am drawing here, I am showing here the diagram with the rays only. So you can see further with the double slit, the rays are going ahead, the wavefronts are going ahead. So at the screen, that point, at the screen, wherever they will meet, I'm supposing that they are meeting at point P. We can take any point on the screen. The lights are superimposing at that point, at every point. But I'm taking a single point, point P. And now we have to find at point P what will be there. Will there be maxima, means maximum intensity? There will be minimum intensity. What will be there? If the two waves from S1, S2, if both are moving at point, if they are superimposing in the same phase or with a constant phase difference, so there will be maximum intensity. And if they are meeting in the outer phase, so there will be minimum intensity. So let's see further in detail. And mostly in the examination it is asked that calculate the width of the fringe, means whether the bright or dark, they both are having the same thickness, same width. So in the examination it is only asked to calculate the width of this fringe. So let's see here the Young double slit experiment, and I'm drawing the diagram first. The source of light, and now the slit is here. From here the spherical wavefront will be proceeding further. Now in front of this double slit, so from this single source, after this, from here it will become two different sources. Like suppose I'm naming source S1 and S2. Since these sources are originated from the main source, so they will they will have same phases, and this distance from S1 to S2, this is actually the double slit. The double slit is what? According to this, the name of this experiment, the double slit is this. So this is the double slit, and the distance from S2 to S1, S1 to S2 or S2 to S1, this small d, remember every name is very special. This is called slit width. Okay, now I'm making this line as the baseline. Okay, further, now what will happen? Let's draw screen first. So here is the screen, I'm naming it the screen, and let this point, the center point of the slit, be point C, and the right bisector it is of the slit is meeting the screen at some point here. Let this point be O. And now I'm going to draw the ray diagram, means the rays starting from the S1, S2 at some point wherever they are meeting. Suppose they are meeting anywhere, and see what is going on here because of the S1, and here S2. Suppose they are meeting at point P. So at point P, S1 and S2 are superimposing, suppose on a screen. If they are meeting, it's superimposing in the same phase, so here it will be maxima, and if they are meeting in out of phase, so here it will be minima. Now let this distance from here to here, from the slit to screen, is capital D, the position from the center, suppose this point from the center is having the distance small x, and if I'm joining from the center with this point P, let this is having angle theta. We are going to calculate with the path difference also. Means we are going to calculate the position of maxima and minima, means you can say position of bright or dark fringe on this screen. To calculate the bright and dark, we need the phase difference. So I don't think that it is easy to calculate the phase difference, but we can calculate the path difference. So see here, what is the path difference here? We can see here path difference. So we have seen in the last day. See this, the equation with the path difference and phase difference. Means if anyhow we can calculate the path difference even, then we can calculate the constructive or destructive. See here, for constructive the path difference should be if m lambda, and for destructive the path difference should be 2m minus 1 lambda by 2. So from this we can calculate also the wavelength of light even. So this is the further part. So first of all, let's calculate the path difference. To calculate the path difference, see here, the path of this light S2 to P, and the path of this light, this ray, S1 to P. So what is the path difference? Simply we can say S2P minus S1P. This is the path difference. So let's draw a perpendicular here in actually to calculate the path difference. Let this point be A. So we can see here S1P is equal to AP. So what is remaining? S2A. So this will be actual path difference, that S2A is equal to S2P minus S1. This is actually the path difference. Again, see why we are calculating a path difference. See here, suppose this source is starting from here and meeting point at O. This is the center middle point of this slit width. It's the center middle point of the slit width, and the second ray is starting from S2 and meeting here, means the path from here to here and path from here to here is same. If the path difference is same, so phase difference will be constant, means here will be what? The maximum intensity. This is called central bright maxima. You can also say central bright fringe. At this point we can say central bright fringe. Why? Because the path difference at O from S1 and S2 will be same, so path difference will be 0, phase difference will be 0, means they are meeting in the same phase. So at this point definitely there will be maxima. Same way we are calculating the path difference, what will be here, then we can say what will be here means maxima or minima. So here you can say this triangle CPO, one triangle, and one more triangle S1 S2A. These two triangle will be similar triangle, and this angle is also will be theta. So I'm using either similar property, or you can say in this triangle I'm writing here. So see here in triangle S1A S2, the using sine theta. See here in this triangle S1A S2, this is, remember that this is 90, means this one is going hypotenuse. So sine theta is perpendicular upon hypotenuse. So what you are getting, S2A upon S1 S2. Let this equation 1. Same way in triangle COP, this triangle COP, in this triangle I'm using the tan theta. Tan theta is equal to, see here, this is the theta in this triangle. That tan theta is equal to perpendicular upon base. What is perpendicular? OP upon CO is equal to OP upon CO. Let this triangle equation 2. So for a very small angle, see this is happening with this slit. In practice, if you can say in the practical work, if you are going to see this will be very fine, like a distance between the two closed needles. The distance, it is very close, means the aperture is very small. So we can say here for small aperture, means theta is so small, theta is tending to 0, or you can say very small. So I'm using sine theta is equal to tan theta. If they are so small, then at that time, so equation 1 and equation 2 will be equal. You can say S2a upon S1 S2 is equal to OP upon CO, or further the S2a is equal to OP upon CO into S1 S2. And now see little bit special. S2a is what? S2a is our path difference. So we are going to calculate, actually we are approaching towards the path difference. So here S2a is equal to what? OP. What is OPC here? O to P, the distance from central bright fringe to that point. This point is at distance x from central bright fringe. So this is x upon CO. See here, C to O. This is capital D. So here it is capital D multiplied with S1 S2. What is S1 S2? See here, S1 S2, the fringe width, small d. So this is our equation for the path difference. So what is the path difference? Just see it here. See here, this path difference. Don't mix the symbol. This is x, this x for path difference, and this x is for distance from the central bright fringe. Both are different. Don't mix them. So if there is maxima, so the path difference will be what? M lambda. So if this is creating the maxima, so S2a will be equal to M lambda. Let's see in the next page. So don't be disturbed with the symbols. See here, position of bright fringes. So I'm writing here again, S2a is our path difference, is equal to x upon capital D into small d. And again for maxima, since maxima, I'm again saying this x and this x is not same. I'm writing in the word to separate them. That path difference is equal to M lambda for maxima. Okay, now the path difference will be M lambda. I'm writing here, this is S2a. What is path difference? So M lambda is equal to x small capital D small d, and this is what the position from the central bright to the position point P. See here, from this central bright fringe to this point P. So this may be 1 2 3 4, whatever it is. So let's name it as this one is what? 0 1 2 3. If it is 0, so first fringe. If it is 1, so second fringe. Same way. So I'm writing here this, instead of x, I'm writing here xm. Xm means first, second, third, fourth. Okay, xm here. So I'm showing xm here also. So you can say M lambda capital D upon small d. So simply what you can say, xm, the position, this is what? Position of the, see here, position of the bright fringes, first, second, third, whatever it is, M multiplied lambda d upon small d. So this is the expression for the position of that fringe, whatever it may be, first, second, third. If we are talking about 1, so this will be 1, 2, this will be second, and so on. So this is the expression for the bright fringes. And suppose at point P there is dark fringe. So for that, what is the path difference? The path difference is M minus 1 lambda by 2, sorry, 2m minus 1 lambda by 2. So I'm writing here. So see again, starting with that expression, S2a was equal to x upon capital D into small d. This was the expression for the path difference. And for minimum, means for the dark fringes, path difference is equal to 2m minus 1 lambda by 2. This was the expression. If you don't remember, see here, see the last expression. So here it was the path difference. So let's fill the value here. Instead of S2a, that we are putting 2m minus 1 lambda by 2 is equal to x capital D into small d. Now I'm writing this in general, so x will be xm. So xm is equal to, on solving you will get m, so the 2m minus 1 capital D lambda upon 2d. But this expression is not looking to this expression, so to make it similar, so we can write xm is equal to m minus 1 by 2 taking that common, 2 common here and 2 after taking 2 common, this 2 and 2 will cancel, or you can say taking 2 inside, so it will be d lambda upon small d. So this is the expression for to find the position of dark fringes. So at point P, whatever the value will be given, we can put it here according to bright or dark fringes. So this is what xm is equal to m lambda d by d, and here xm is equal to m minus 1 by 2 d lambda by d. But in examination it is asked to find the fringe width, means see here the bright and dark. In examination you have to calculate the width of this bright or dark. You can see this all are of same width. So let's calculate the fringe width. Suppose these are the fringes. Suppose 1, 2, 3, 4. Suppose we are knowing the distance from here to the fourth one. Suppose this is x and x1, and we are having the distance value from here to this one, say x2. So what will be the distance between them if I am subtracting x1 minus x2? So this will be remaining. Same way as we have having the expression for the bright and dark. So I am talking about the bright one. So x1 we are having, xma we are having. So I am writing the first. Suppose we are having the first fringe. So m instead will be 1 lambda capital D by small d. See this expression. This was the expression putting x is equal to 1. Now going for the second one, x2. Little more distance from the central bright. What is central bright? See again. From here I am going ahead. x1 suppose somewhere here, x2 somewhere here. So x2 is equal to twice lambda d by small d. We have to find the width, that is called beta, with the symbol beta, fringe width. I am writing here fringe width. Beta is equal to what will be here, x2 minus x1, and that will be this one. And after subtracting, beta will be what? Only lambda d by d. In examination it is used to us to find the fringe width. What is the fringe width for? This is the for bright, but I am saying that the fringe width all are having the equal width. So as we are getting the expression for the bright one, same must be coming for the dark one. Let's see. So see, this is the expression for the dark fringes after putting the value that for the first one, x1 is equal to 1 minus 1 by 2 d lambda by d, and for the next one, if I'm talking say 2, so this will be 2 minus 1 by 2 d lambda by d. Now fringe width beta will be equal to x2 minus x1. After putting the value, you will get again that d lambda by small d, the same fringe width. Either you are doing for the dark fringes or for the bright fringes. Here I'm ending this lecture. In the next lecture we will see the conditions for the interference and some other topics and some numerical also. So till then, take care, be safe, and thank you.